All right, and I think we're going to do 9.5, probably I think together with 9.6, it looks like, based on the sections. Yes, 9.5, 9. We're going to do 9.5 through 9.7 all as one section. Yeah. All right. So 9.5 through 9.7. That's what we're going to be focusing on. All right, so 9.5 through 9.7. This is where we finally get the conservation of momentum. But we talk about conservation in the sense of it's always going to happen with momentum, but not always going to happen with energy. Do you remember from last year when we had two types of collisions? Yeah, elastic and inelastic. So let's start by saying that momentum initially is always equal to momentum at the end. This is always true. Always, 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 always. Okay, so momentum is a constant. P initial equals P final. But energy loss or energy change is not always going to be the same. So we have those two scenarios, elastic and inelastic. Here's how I remember them, because when I was your age, honestly, I would confuse the two. And if you confuse the two, it's a really big issue, right? Because you're using the two wrong things. Elastic. Things that are elastic. Things that are elastic. I think of things like things that bounce off of one another very easily. Like a bouncy ball, a pool ball. Something that rebounds off of something else. Because I think of elasticity, coefficient of restitution is the amount of the energy that is bouncing back up off the ground. So for elastic, think of bouncing off objects. For inelastic, think of it being embedded in the other object. Okay, like the ballistic pendulum problem, which is what you guys are actually focusing on right now for Science Club, which we're going to focus on here. We're going to talk about that. But elastic is where they hit each other and separate afterward. The best example of elastic collisions, not the best, but one of the best, is pool. Actually playing pool. Now, there's a lot that goes into pool. The ball rotates. There's more than just this. But the concept of those collisions, it's pretty close to elastic. It's not perfectly elastic. It's in between these two.
It's not like the Newton's cradle.
Yeah, very much like Newton's cradle. Yeah, that's another great example. Newton's cradle is very close to being elastic, which is why what?
It goes through.
For a while, right? Eventually, though.
It like slows down.
Yeah, because it is partly inelastic. Those marbles are losing energy at a very, very, very low speed or a very low rate, the energy loss. Where is the energy loss in Newton's cradle? Sound.
As it transfers between the marbles, right?
Careful with that. I need more of a clear statement.
Air resistance.
Air resistance, sound.
Heat. Like that's
Heat.
like the friction between each ball when they move.
Okay, so friction or deformation. I know there's very minimal deformation, but there is still deformation of each collision occurring. And that's kind of what you were talking about, the transfer there. When you say transfer,
Yeah.
transfer means keeping momentum, So
Yeah.
be careful with that phrase. So there's definitely air resistance, there's definitely sound, there's definitely deformation in the ball, there's some frictional loss when it hits. One other spot where we lose energy in Newton's cradle.
Like tension.
Yeah, the rope itself. The rope itself. Okay, so the tension in the rope means that there's going to be a pulling force on the eye hook. If you want to look up there, you can see the eye hook up there. And the rope connected to the eye hook as it swings creates friction. We were talking about it today. Chris and I were talking about this for a ballistic pendulum, and he said maybe we'll use bearings at the top so that as this thing moves back and forth, there's very little friction. Okay, to reduce the amount of frictional loss. But those are the areas you'll lose it in Newton's cradle. In general, though, in elastic collisions, you account for the loss in energy. Elastic, we don't account for the loss. So for elastic, if we don't account for loss, we could say that this equals this. But for inelastic, we would say this does not equal this. For all inelastic processes, it's a loss in energy. So we could write that as the following. We could either write, if we want to, K0 equals K plus the work done by friction in absolute value terms. Even if it's negative, we're going to consider that to be a positive value here because we're adding it on to what we have at the end. Or we could say this. where this is assumed to be a negative quantity. I don't like to move it over. I don't like to write this as a negative. I like to write it the way it's written here and saying that you have kinetic energy plus a negative amount of energy giving you what you have at the end, which is lower energy because you've lost energy. Or you say you started with a lot of energy, you end with less, and how much is missing is what's over here. Okay, that's why I'm putting absolute value over here by work done by friction, whereas here I'm leaving it as work done by friction because that would be a negative quantity. But I need absolute value to make it positive on the right side, obviously here. But that's the general concept that we're going to look at for the next sections, 9.5, 9.6, and 9.7. This is literally summarizing all three sections here. They kind of take you one step at a time. Okay? So let's do a couple example problems so we can see this kind of at play. The first example problem is a pretty simple one. Okay, so let's start with that. And the example problem says the following. And we don't have to do the exact wording of it, but here's the scenario. You've got an object. It's moving forward. Then suddenly there's some separation. Okay? So the object's moving forward, moving forward, moving forward, and then something is fired in the reverse direction from that object. Something's fired in the reverse direction. Or something's fired in the same direction, either way. What can we conclude from something like this? Let's say this velocity here was something like 10. We can automatically recognize that this velocity, what do you got, Chris? Greater than 10. And I should maybe draw my vectors accordingly then, right? Maybe make this guy nice and long so we can see that better. I'm not even drawing forces, just velocity. Why is it greater than 10? Why must it be greater than 10, Chip?
Well, I mean, if you're firing in the opposite direction of something off of it, you're like putting a greater normal force on it, and thus it has to accelerate it in that direction, and therefore like the velocity has to be greater.
Not normal force, but yes. Everything else you said sounds great. It's recoil, right? You know recoil? If you've ever fired a gun, or if you've ever fired something at all, or even if you've ever I'm trying to think of another example. Even throwing something, like you take a baseball, like really throw it, you feel your body kind of like kick back a little bit, and the torque that you're providing when you throw it, it actually kind of helps the ball go forward by you pulling back. So the concept is this: it's got some momentum to start, right? Whatever the momentum is. Let's say that the mass of this is 20. So we have a momentum of the system of 200 to start. And then after the explosion, we have to consider what's happening. Okay? Well now, let's say that this becomes 19. And let's say this is 1 then, obviously. Let's say the velocity going back for the projectile with a mass of 1 is 5. And our question is, what is this v, right? We know it's greater than 10, but let's say, what is the velocity of the object now? And the key is to recognize that if it's propelling it backward, what kind of a velocity momentum is that? It's propelling that little object backward. So what kind of a velocity is it? What do you think? What do you think? It's backward, Chris?
Yeah.
You had your hand up, sorry. Was that a hand up or no? You're just stretching.
Yeah.
Oh yeah, so if it's propelling backward, what kind of a velocity must it be? A negative velocity. That's the whole key to this problem. Vectors matter for linear momentum. Remember energy? Last chapter? Did direction matter much with energy? Energy is a scalar quantity. Kinetic energy, potential energy. Potential energy stored in a spring, 1/2 kx squared. We never had a negative value because of direction of energy. All we accounted for was negative as in like a loss of energy, right? But not directional. Here, direction matters. So the momentum of this object is going to be mv, and we'll say this is like m1v1 plus m2v2. But in the beginning, we just had mv. But now it splits into two parts. Right? We did 20 times 10 earlier to get 200. Now we've got to do, for this one, the mass of the little thing projecting backward is 1. Its velocity is -5. The mass of the second part is 19. And we're trying to find out its velocity, v2. But the key is that we know what this will sum up to because we had the momentum in the beginning of the problem. Pat, what was that momentum in the beginning of the problem? 200. So you know what? That means that this quantity has to be equal to 200. The momentum initially equals the momentum at the end. So therefore, this V2 has to be greater than 10. It's not going to work if it's not. What do we get for V2 in the end? If we add 5 and then divide by 19, right? That's what we would be doing. We'd be adding 5 and then dividing by 19. What's 205 divided by 19 going to give us? 10.8? Is that what it is? Okay. Again, we're setting this equal to 200. This is equal to 200. And again, it's because the initial momentum equals the final momentum. Conservation of momentum at the top. All right, here's a question for you. Follow-up question. Is this elastic or inelastic? Give mathematical evidence.
Elastic because initial momentum equals final momentum.
What do you think? You all agree with her? I don't. Careful. That's if initial energy equals final energy that it's elastic, right? It's energy that tells us elastic versus inelastic. You thought of momentum, be careful. So what I'm saying is, you can't really tell unless you calculate. We don't know if this is considered inelastic now. I can tell you now that it's going to be inelastic. Because usually explosions or collisions where things stick together, those are inelastic. Because it must take energy for those things to deform. The shape is deforming. So it's going to be inelastic, but we want to prove it. So let's find the kinetic energy of the object in the beginning. What do we got? 1/2 mv squared in the very beginning. What do we get for kinetic energy? 1/2 times 10 times 20 times 10 squared. 1,000. 1,000. It's all right. Is that, are we all in agreement with that? We checked our numbers, right? 1,000 in the beginning? Okay, now give me the kinetic energy at the end. We have 2 objects now, though. 2 objects at the end. So we've got to look at the kinetic energy afterward and say, okay, 1/2 m, m is 1, v squared. Remember, for energy, the negative doesn't matter because we're squaring it. Plus 1/2 m times v squared. What are we going to get for our energy comparison here? So we've got 1,000 up top, and then what are we going to get down below here? 2 objects, both moving, both have energy. We have to sum their energies together to see how much energy is in the system afterward. Chip's the calculator guy today? All right, it's fine. Go ahead, Chip.
1,176.2.
Yikes. Correct? Incorrect? Correct? Incorrect? I'm trusting you right now, but I'm just asking for verification, right? Thanks, I'm not trusting you.
I'm gonna say it's correct. I'm gonna advocate for myself because the work that's gonna be done by friction or whatever it is gonna be the absolute value. Should be greater than the initial.
What did you get?
1120.
Yeah, I got 1120.
What'd you get?
1120.
1120? 1120? Still greater though, right? That's what we're noticing. So what's the deal here? What's happening? How is it possible that we have more energy afterward? How is that possible? Chris? when we round it up.
velocity.
What do you mean? I don't think it creates that much of an issue. 1120, right? That's the number we're talking about? That's a huge difference. I don't know. You're talking about the 10.8, Chris, right?
Yeah.
And what was it? It was like 10.77 or something, probably?
Yeah.
It's probably not that, but I like the idea. What do you think? How could we have more energy afterwards? What's that? So what kind of energy did the system have in the beginning that we didn't account for? Yeah, it's got some sort of chemical potential energy. We're not going to get into chemical energy, but the idea of it is that for an explosion to occur, you're going to have some sort of energy stored in the bomb. We use the phrase bomb for now, right? Okay, you have something stored in the apparatus that causes it to explode. So in this case, there must be some sort of chemical energy that was in the beginning of the problem to cause a difference in the kinetic energy from the beginning to the end. Now, what if we had a lower value in kinetic energy afterward? What if this number were lower? Forget the scenario, which is in general. What if there was a collision or an explosion or something happens and there was a lower number? What can we conclude? What could the reasoning for that be? If it were lower as a number. If it were lower. What do you think? Check that.
Like things collide and stick together and they like continue moving.
Mm-hmm.
Or maybe they're moving like opposite direction, but in the same direction. I mean,
And what would cause that loss in energy specifically? What would cause? You're right. What would cause the loss in energy? If they stick together, what causes it?
that difference in velocity, I'd say. So
Conceptually, not mathematically. Conceptually, what causes a loss in energy if two things stick together?
deformation.
Yeah, deformation, fusion, heat. Have you ever seen a car accident where the bumpers stick together afterward? Or the front end of a car kind of gets wedged into the back end of another car like that? A lot of rear end accidents that happens, and the bumpers will physically fuse together. There's such a high impact of velocity that there's enough heat generated that they'll actually fuse, like welding, fuse together. And that'll cause a lower energy afterward than the energy it had to start. The key here is this again. A difference in KE means inelastic. It means energy must have been lost or used up somewhere along the way. There must have been some sort of energy change occurring here. Form of energy. It's not just kinetic anymore for inelastic. When it's elastic collisions, the kinetic in the beginning will equal the kinetic at the end, and you'll say that there's no loss or gain in kinetic energy because the system was an isolated system, if I use the phrase, isolated. Okay. All right, there are a couple equations your book writes down, and these would be useful ones to have in your calculator. They're not on your formula sheet, so I'm going to jot them down for you. Okay, and this is on page 237 to 238. This is for elastic collisions. For elastic collisions. Let me just make sure I'm right with this phrase. All right. So this is the general, let's just say elastic with object 1 attacking object 2. So diagram wise, okay, this is what we're looking at. Object 1 is attacking object 2. Object 1 hits object 2, causing object 2 to move forward, and then object 1 either continues with it or gets rebounded. That's why I put question mark there. It could go either way. Object 1 might hit the first object, and if object 1 is big enough, it'll keep going after it hits the first object. But if object 1 is really small, it'll rebound off. Think about like a 3-year-old running into a parent, right? Ever see like a little kid literally just run to an adult? Sometimes they'll run into them and just boom, bounce right off them. Because they're literally like a wall compared to a kid. So a really small object attacking will get rebounded off. But a large object will continue forward. Now, if it's exactly the right size, what will happen is, here's what happens, ready? It's pool. You hit the cue ball hits the other one starts to move, and the cue ball just stops. It's rare that happens, right? You hit low on the cue ball, the ball comes back, you're drawing it back, we call that English, you spin on the ball. If you hit higher on the cue ball, it puts a little front spin, so when it hits the ball, it'll continue afterward. But if it's going toward a pocket, you don't want it to continue afterward. When the ball just collides, and then the other one moves, and this one stops, that's the in-between. So there's 3 scenarios. The little ball could either get rebounded off, or it could be a bigger ball and continue following, or it could be exactly the right size, hit the second one, and just stop there. Okay? And again, this is elastic collisions we're talking about. So here's the equations. So V1, they're calling it F for final. The velocity of the first object after the collision, the generic solution for it, is m1 minus m2 over m1 plus m2, all times the initial velocity of object 1. And this is combining conservation of momentum and conservation of energy. I'm using both concepts to make this true. And then the second object's velocity after the collision is given as 2m1 over m1 plus m2 times, again, v1 initial. So these 2 formulas can be really useful for an elastic collision on a multiple choice problem. You don't want to have to derive them and go through the process. What I'm really doing here, or what the book is doing, and I'm showing you here, is they're combining these 2 equations up top. Here's the 2 equations. So they're combining conservation of momentum, which is written up the top there, with conservation of kinetic energy. So those 2 equations written at the very top, with a lot of algebra and substitution method a couple times here, you get to these 2 solutions down here generically. We're literally solving for V1F and V2F, but it's in a couple spots, so it's just going to take a little bit of work. Okay? Again, this happens on pages 237 to 238. They don't even show the substitution really here. They kind of show it at the end. They say, after dividing and with some more algebra, we get to this solution. It's not a difficult thing to get to, but it'll take us 10-15 minutes just to derive it. There's no point in going through the derivation because it's not something that you're going to want to have to derive on a test anyway. So I would recommend having this scenario as one of those scenarios in your calculator. So when you get to a problem in multiple choice and it's an object or it's an instance where one object is attacking the other, think about which scenario or which case you're looking for here. They give 3 outcomes for this.
So it says, does
Yeah.
that equation go to the first scenario?
So this is the velocity of the first object after the collision. This is the velocity of the second object after the collision. Yep. And Kara, based on the masses, we don't know whether to move left, right, or stay still. And those are the 3 scenarios I talked about. And your book outlines all 3 scenarios. They talk about if the objects had equal masses, completely identical masses, like the same ball, billiards, pool, the initial ball will stop. So let's go through the 3 scenarios now. I'll put them up one at a time. Okay? So scenario 1, let me move this over a little bit so I can see on the screen. Scenario 1, come on. If M1 is equal to M2, then the first ball will stop, and the second ball will take on the velocity the first ball had. Again, if the masses are the same, and think about it logically, right? Look at the equations, people. What's m1 minus m2 if they're the same mass? What is this going to become? 0. So 0 times anything is 0. How about over here? Take a look over here. If the masses are the same, double m1, well, this would be m1 plus m1, right? If they're the same. So I got double m1 over double m1. Those cancel. I'm left with v1, 0 for this one. Okay, so when the masses are the same, these are the two results we get from those equations. If the attacking body is greater, then V1F is still going to be going in the same direction. How do I do that? Let's say it follows or trails. V1F trails object 2. V2F is approximately double the initial velocity. Let's put an approximation symbol there. Approximately. Okay, V1F trails object 2. In the third scenario, if the first object is less than the second object, then V1F rebounds off of object 2, and V2F, this is an interesting one. This comes out to be, this is probably not one you're going to have to even write down or memorize, but just so you know what it is, times, that's what it comes out to be. And this is an approximation again here. Okay, approximation. The book then specifies another, give me like 10 more seconds here. The book then says a little bit more. It says, like, if the masses are much, much different. How do you write much, much different or much, much greater? Not just greater than. What's the much greater than symbol? Anyone know? Math, the book uses it. Uses a calc now? A double symbol? So greater than symbol twice means that mass 1 is far greater than mass 2? I know, it's kind of ridiculous, because what is far greater, right? It's all relative. But if mass 1 is much, much greater than mass 2, then although it's going to trail the second object, it's not going to lose much velocity at all. It's going to pretty much maintain the same velocity it had. If the second object is much, much greater than the first object, it's going to rebound with pretty much the same velocity it had in the negative direction. Okay, but the idea is that it's going to rebound or it's going to trail. That's the key to these problems. Over the weekend, I think I gave you guys some homework, right? I think I gave you homework in 9.4, 9.3 to look at. Okay, so catch up on 9.3, 9.4. This is 9.5, 9.6, 9.7, and I'll give you an assignment for that. I'll add that to the regular assignment and to the problem set. Okay, you have problem set questions up already. I will also try to start sending you out a couple of different problems of free response to practice. The free response are very much not going to be just momentum though. This is where we start getting into a lot of problems that are combined, where energy transfers to momentum, and then the momentum transfers to kinematics, and you have to find the range of the object. So the free response, you're going to be putting together all of the topics you've learned this year into these free response coming up. So I'll start with that maybe next week. I'll give you the free response. But over the weekend, get yourself a good head start on 9.3, 9.4, and if you have time, I'll start putting up 9.5, 6, and 7 for you to work on.